So, thank you for joining for the first lecture on our course on laser physics on the chapter 2. So now the lecture will be about time-dependent perturbation theory. And as the name doesn't really suggest, the main idea here is to introduce you a means to really quantitatively calculate how the dynamics of population of these electron states within our laser gain medium can be really calculated. So basically, we really are now about to introduce to you the mathematical framework, how we can calculate the population dynamics of electrons. So that's the main thing here. So what we will do is that we will develop, as I already mentioned, the necessarily mathematical framework to understand and calculate the atomic cross sections and understand the dynamics taking place within our electron system. And we need to use a few assumptions, and for simplicity, we only consider the simplest possible atomic system, and that would be the two-level system shown in this figure. So what happens in our framework and the model we are interested in solving is that we do have the ground state labeled with G or number 1 here, and then we do have the excited state labeled with 2 or E as in the excited state. We are thinking that we are exciting or perturbing the system with a photon with an incident energy corresponding to omega naught, and that of course corresponds to the energy difference of these states for the electron. That's what happens, and of course after perturbation you may have scattering of light or absorption and so forth. Okay, so what we do is that like always when we try to understand quantum mechanically how electrons are behaving and other quantum mechanical objects most of the time, we go and solve the Schrödinger equation. So we write first a system that is perturbed by an electromagnetic interaction. So we write in Hamiltonian formalism for a Schrödinger equation. So we have on the left-hand side imaginary unit times the h bar times the ket of our electron wave function here, and on the other side we have the interaction Hamiltonian or the total Hamiltonian interacting on the state vector. So here h hat is the Hamiltonian operator, so that tells us all about the dynamics of our system, and this ket of the wave function psi is really a state vector that represents the system that we are looking at. So basically like how the electrons are moving back and forth in this two-level energy system. Okay, if the system doesn't really interact with anything, so we would not have any impinging electric field, incident on the system, then the Hamiltonian operator would be basically just a time-independent Hamiltonian. And then if we would solve the system, the Schrödinger equation, then we would be knowing what is the system's total energy. So essentially, what is the kinetic energy plus the potential energy, so that the Hamiltonian would be of this form. And sometimes we use this kind of node sub-index notation there to kind of denote that this is the kind of like interaction-free atomic Hamiltonian, and this consists of the kinetic part and then the potential part, and those hats there denote that we are speaking of operators as we do in quantum mechanics many times. Okay, and now we have the system interact with a field. So essentially we are having an external perturbation, and in our case that is the electromagnetic field that is incident on the system, and then we must really change the Hamiltonian. So we must modify that into the total Hamiltonian. Then that is the sum of the atomic Hamiltonian h naught plus the interaction Hamiltonian, describing the external perturbation into the system. So how the electron wave functions are being modified and how possibly some kind of dynamics within the states is being created due to this interaction Hamiltonian. So h naught is the atomic Hamiltonian. H hat interaction accounts for the interaction between the electromagnetic field and the electron we are considering. Most of the time, we are happily just assuming that we are under so-called electric dipole approximation. And in this case, we just mean that the interaction Hamiltonian is written as the incident field E times a dipole moment operator mu. So here E is the incident field and mu is the electric dipole moment. So this is what we mean oftentimes when we are saying that we are under electric dipole approximation. So the Hamiltonian is only this. So there's, for example, no interaction due to the magnetic field, or there's no interaction due to the fact that there would be strong gradients in the actual incident field. So only we consider a local response operating on the electric dipole moment, and that's it. That's the kind of interaction that we are considering with. Sometimes we need to go beyond into this and consider so-called multipolar light matter interactions, but that is not the case we are interested in this course. Okay, so considering that we don't have any incident electromagnetic fields, so we are now really just wanting to solve the atomic Hamiltonian Schrödinger equation, we can really use time-independent Schrödinger equation to solve the system and calculate the eigenstates without perturbation, and this basically results into an eigenvalue problem of this form. So we have the H0 hat, so that's the atomic Hamiltonian, and then we have a state ket. K can be either G or E, like we have a two-level system, so either the electron is in a ground state or in excited state, and then since this is an eigenvalue problem, then we have a E, the energy associated with this given state, and then we have the ket of K, where of course the K can be either G or E, as I already mentioned. So this is basically an eigenvalue problem on here side, this side. This often looks like a matrix. Here we have a vector, and on this side we have a scalar and we have a vector, and this is how the eigenvalue problem is being formulated. So in a way, what this eigenvalue problem tells us, the mathematical structure here, is that if we are operating with this vector or let it pass through the Hamiltonian, essentially the outcome is still the same kind of vector, so that the state is not really changed, that only some kind of modification is being done for the actual amplitude. Eigenstates, in our case, they can be described by full time-dependent wave functions. I don't go into the details of showing how this is being solved. I think you have already done this in the kind of rudimentary quantum mechanics introductory courses, so it's of this form. So we can see that there is some kind of amplitude there, denoted with a smaller phi or psi, and then we have a oscillating term depending on the energy of our state. This gives us a possibility of calculating the actual probability densities. So of course we can take the square modulus of this wave function, and essentially the oscillation then disappears, and this is what we get out. And we see that this is actually independent of time, and this is also explaining why sometimes these states are called stationary. So nothing much happens in terms of the dynamics when we are only considering the atomic Hamiltonian and solving the Schrödinger equation. Note for the mathematics, if the system is in one of these stationary eigenstates, this kind of equality falls. So if you look at the kind of time change of any kind of expectation value, and A here can be of any operator, this is basically equal to 0. So nothing really much happens in terms of dynamics in our system. And this really applies for any possible operator we can understand or consider in our system. So this is basically what applies for stationary eigenstates. And many times when we are doing quantum mechanics derivations of things, this kind of like a mathematical identity can be used to simplify calculations. Now, stationary states, they also form a complete basis, and this is an extremely nice property for the kind of mathematical structure we're dealing with, so that this really helps us. And now we can really represent the total wave function. So basically, in what kind of state the system is. Will our electron be in the ground state, or will it be in the excited state, or will it be in a superposition between these states? So this is basically the kind of total wave function, and we can like describe it using a sum of these stationary eigenstates. So at any time, we can basically write the total ket of the wave function as a sum over all the states, all the k values, where ck is a kind of a expansion coefficient, and then we do have exponents that they show that we have a kind of oscillation in our wave function or eigenstate wave function. So this is basically kind of like a way just say that we can form a complete basis using the stationary eigenstates. So here CKs are the expansion coefficients I already mentioned, and of course if we would do the math, these oscillationary terms, the exponent I something there, really they vanish when we would take the square modulus. So these expansion coefficients and their square modulus give the probability of the system of occupying a given eigenstate. And then normalized, these are normalized in such a way that if we take a sum of the square modulus of these all expansion coefficients, we get a unity out. So physically, of course, this just corresponds to a kind of like a sentences such as the electron has to be somewhere. So either the electron has to be in the ground state or in the excited state. And when we are summing the square modulus together, we get a unity. So the electron really has to be something. It cannot really vanish from our system. Now, let's get forward. So basically we have a description for the total wave function for a two-level system. So basically we can write everything explicitly in this kind of form. So basically it's a kind of superposition for the electron to be either in a ground state or in the excited state. So either it could be, for example, in the ground state, and then this CG would be unity and this would be 0, or it can be either way, for example, totally in the excited state, or of course in the most general case, we will have a superposition state. And here we define the resonance frequency of the atom, omega naught, in a form that's basically just the energy difference divided by the h bar. So this is a kind of like a way to really represent the wave function. And now we can start considering how we can perturb the system with an electromagnetic field and really solve the system of interest. So let's do some further approximations, or actually assumptions. So let's again state that we are under electric dipole approximation. So we are interested in a dipole interaction, so that the interaction Hamiltonian is of the simple form, so that basically the interaction Hamiltonian is just the incident field multiplied with the electric dipole moment operator. We are interested in classical electromagnetic fields, so we don't want to deal with any quantized fields. So any classical field is fine. And for simplicity, we consider X-polarized incident field. This is, of course, like we could do for any kind of arbitrary polarization, but this helps out the mathematical calculation. So let's just do this in our simple calculation we do here. Now, for conceptual simplicity, of course, we can also just consider monochromatic plane waves. And as we already mentioned, we have X-polarized field. So basically this vector field is only pointing or oscillating along the X direction. Then we have some given amplitude, and then we have the propagation of the time harmonic plane wave. And please note here, this partially modifies why this electric dipole approximation is valid. If you look at the real atomic dimensions of interest, and this is really what we are looking at, this is the system we are looking at since we are kind of considering atomic gain media, the dimensions are extremely small compared to the incident wavelength. So this is basically of the order of some hundreds of nanometers. So Bohr radius AB is essentially of the form of a kind of some angstroms, and this is a lot smaller number than the incident wavelength lambda. So basically what the atom really sees is that it sees a locally constant field, and this is the kind of usual justification why we are happily in assuming that the electric dipole approximation holds. And most of the time this is an extremely good approximation to make. Now, okay, let's consider the electric dipole moment. Interestingly enough, this operator here has odd parity, and what odd parity actually means, it's a kind of a symmetry operation or a symmetry property, and it just means that this operator changes sign under inversion symmetry. And this is, I cannot really go into the details of the importance of this kind of structure in the mathematics we're dealing with, but symmetry properties are extremely important, and they essentially kind of dictate, for example, are some processes allowed or are they not allowed? And that's why we want to kind of show you a little bit about this mathematical structure, so that you kind of start understanding that why we have some kind of selection rules in specific transitions and so forth. But okay, let's get forward. Basically, electric dipole moment has odd parity. So what this means is that when we are changing the displacement vector, so rk, into minus rk. So we do perform an inversion symmetry operation. Also, the sign of the dipole moment changes. So the mu changes into minus mu. What this then means is that then the interaction Hamiltonian is also, it's proportional to this electric dipole moment operator. So also the interaction Hamiltonian has the same odd parity. And now this implies that when we are doing these calculations, physically we only connect atomic states that are having a different parity together. So let's go with an example here and what this, for example, implies for the kind of like a behavior of the excited state and the ground state when we are not like really moving electrons back and forth. So for example, if you do a calculation of the expectation value for this electric dipole moment operator and how it looks like in the ground state, so basically like we would calculate the expectation value of the interaction Hamiltonian with respect to the J state of G. This we can sometimes use a kind of like a simplifying notation. So we just define that this kind of piece of mathematics looks like this. So we just define X operator this way. So it's equal to this. And then this equals to 0 due to the fact of odd parity in the interaction Hamiltonian and the symmetry properties of these ground states. So basically, like I already was trying to say, we are just using this kind of shorthand notation here so that this kind of like Xij basically just means that we are really taking an expectation value of like a J state going and being transformed into the I state. So this is basically just mathematical definition, simple like kind of shorthand notation. So this kind of value can be written in a similar way using integral notation. So basically this bracket notation just corresponds to taking an integral now in a specific kind of basis that we are now describing the state vector for the ground state in a specific basis for R, and then we are calculating the interaction Hamiltonian overlap and then multiplying that with the G star. So basically now what we have mathematically is that like I already mentioned, here this interaction Hamiltonian has odd parity, and then this ground state, it has even parity, and similarly the other like complex conjugate that we get by operating on the bra here also has the same symmetry properties as the actual ground state. So we have even times odd, even times even function is an even function, and then we end up with an integral over an even times odd function. And if you look at the Wikipedia result, we realize that this is actually identically 0. And this is because the interaction Hamiltonian is odd, the ground state is even, and then this gives to a result that we have an even function. So basically, this is the kind of end result. So we don't really have any kind of like expectation value for electric dipole operator in a ground state. We can repeat the same thing for the excited state, E. And now again, we have a vanishing integral, the same thing with using the same notation of capital X, EE. And we see that this is the case because now the excited state has a different parity, and then the multiplication of two odd functions is an even function. And again, we have an identically 0 value for the integral. So here again, now we have a higher electron state. So this actually has a different parity than the G, the ground state. So now we have 2 times odd functions within the integral. That gives us an even function, and then we have this odd times even thing going on again, and the integral is identically vanishing. So basically this means physically that the state that we consider does not have any permanent dipole moment. So the electron, when it's only in the ground state or when it's in the excited state as such, there's no permanent dipole moment. If there will be a dipole moment, it arises due to some kind of transition. So when for example, the electron is being raised from the ground state into the excited state. Of course, if we branch out into off-topic considerations, like we could start thinking that are there then systems that would have a permanent electric dipole moment, even in the case of a kind of like a just electron residing in a ground state. And then somehow, like I guess one starts thinking ferromagnetic materials, that are there materials that would have a permanent electric dipole moment within a ground state. So are there something known as, like, I don't know, electro or permanent materials or ferroelectric materials? But I guess these kind of discussions will be left to the kind of group discussion exercises during the campus time. So basically, I just wanted to branch out with these kind of like symmetry thoughts and the mathematical like example we provided here, that maybe it is interesting for you to kind of Google a little bit what would be ferroelectric materials, are there such materials, and what are the implications for applications and technology. Okay, now we are like almost there. We just really need to solve the actual system, so we can now put everything together and really look at the electron dynamics in this simplistic two-level system. So we have this Schrödinger equation of this form, and now we are really in a kind of like location where we can place in the actual form for the interaction Hamiltonian. So this is how it looks like, and then we have described how the total wave function looks like, and this is the kind of superposition of these two possibilities for the electron to reside in either in the ground state or in the excited state. And now we consider incident frequencies omega of the incident field that are close to the transition frequency omega naught. And this basically like gives us a kind of tools to simplify calculations further. So this is what we are assuming, that we are basically having incident field with a kind of frequency matching almost with the transition energy of the electron being lifted up from the ground state into the excited state, or being either way stimulated, emitted, or stimulation emission taking place and kind of lowering the electron from the excited state into the ground state. Okay, so let's assume that we are working next under a so-called interaction picture. So basically we are now more interested in just like looking at the dynamics of the electron state with respect to each other, and not a kind of like a stationary coordinate system with respect to time. So we can really simplify the dynamics associated, and we don't really need to deal with the kind of like a dynamics and oscillations arising from the unperturbed Hamiltonian H naught hat. Now we can substitute the last two equations into the first one, and we can also simplify math by basically projecting onto these different bra states and use these kind of identities we discovered previously, so that the kind of like expectation value of the interaction Hamiltonian at the ground state is 0, and the same thing for the excited state. And now this results in a system of coupled ordinary differential equations. So the Schrödinger equation in a two-level system can be basically then written explicitly in this kind of form, where we do have the hats there showing that we are taking a time derivative of our expansion coefficient. So we are like having two ordinary differential equations. They are coupled together. So here we have a time derivative of Cg, and here we have a Ce here. So we see that these differential equations are coupled. And then here we have a so-called Rabi frequency, which is essentially this kind of quantity here. So we must calculate this kind of interaction Hamiltonian calculation. And then we have cosine oscillations, and then we have also oscillations at the omega naught frequency. So here omega is known as the Rabi frequency after Isidore Rabi, who was working a lot on atomic physics back in the days in the early 900s, 20th century, so 1930s and so forth. Okay, many ways to solve this kind of coupled system, and of course the easiest one I would say would be to just like use a ansatz and do brute force verification that the trial function works. But let's do this by the second easiest option, because this is more powerful in terms of doing other similar calculations. So let's go with the power series expansion of the C coefficients with respect to the Rabi frequency omega. And this is basically an interaction parameter. And these days, AI will give you lots of like a useful and semi-useful input regarding power series expansions of different kinds of functions. So if you are in doubt, maybe you could talk for a while and chat for a while with an AI to understand how you can perturbatively solve many differential systems using this kind of approach. And you can see more kind of like other examples how this math works. So let's assume that the electron is initially in the ground state. This really helps out the derivation. So basically we have some kind of initial conditions to solve our differential equation. And this mathematically, of course, means that the CG parameter is basically unity, so that the electron really is initially at the ground state. And since it's there, it cannot be at the excited state, so that CE expansion coefficient at the time 0 equals 0. And this is the initial condition we use to solve the coupled system of differential equations. And now we assume this is the power series expansion approach that we take, that we can really write this expansion parameter CG in a kind of like a power series expansion form. So this is basically how the math looks like. So let's go one step back here. So we have this CG, and this is the total expansion coefficient for the electron at the ground state as a function of time. And we assume that this perturbation into the system due to the electromagnetic field is weak enough that we can really consider this kind of perturbative approach, and we can write this term using a power series expansion. So basically we are really taking a power series expansion, writing this total CG factor as a sum over different terms of varying order, of increasing order as a function of this Rabi frequency order. So basically we are writing this kind of summation term, and this would be corresponding to our total CG. So this is our assumption, that the perturbation is weak enough that we can really describe everything like this. And then we can write the same thing for the CE terms, and exactly the same kind of terms arise. And this is our approach that we use to solve things. And now we can iteratively solve the system by substituting this kind of ansatz little by little into the above equations and solving each in terms of increasing order with respect to the Rabi frequency. So basically, second, we will be ordering these terms in the matching orders of Rabi frequency, and then we solve each of these newly formed coupled systems one by one, starting from the lowest order. So that would be the kind of like N1, because the N0 case is pretty trivial, following from the initial conditions. So basically the 0th order cases would be expansion coefficient terms like this, arising just from the initial conditions. Okay, let's now use these lower order solutions to solve the next higher order terms. And then this approach is being repeated until enough terms have been solved. And then we stop the derivation and we are happy. And then we say that we have been solved. We have solved the system up to a given order. How far we have went, I don't really know. Depends on the cases, but that's the approach. For example, in nonlinear optics, this is a very usual approach to understand how do we have, for example, second order nonlinear processes, how do we have third order nonlinear processes, and so forth. So most of the time, we can really use this kind of perturbation expansion approach to calculate what happens under light matter interactions when we are having a relatively strong incident fields, so that we are not under a linear approximation anymore. Okay. So let's now solve our case up to the first order. So that would be to the Rabi frequency of the first power, so omega to the power of 1. And explicitly, of course, we still have those coupled differential equations. So we can now plug in these different terms in these like a CG and CE terms. And this is basically what we get out from that. So we start and we put in the first order like a term here. And then we have the omega multiplied once here, and then we place in here also our first lowest terms in terms of CE, and this is what we get out. And now we see this is a 0, So only kind of term that we get out depends on the second power of Rabi frequency omega here. So this is actually a kind of higher order term already. Oops. So that this basically is too high in terms of order of Rabi. So we will say that this is basically 0. This is not of interest for us. Now the second equation here, it's similar kind of math, but the end result is slightly different. So basically what we have now is that we place in the first order expansion term for the CE and calculate the time derivative. And then on the right hand side, we have the first terms like this. This was the unity case here because we do have in the initial conditions saying that in the beginning we have like an electron at the ground state. So this is unity. And then again, this is not. But on the other hand, we have our multiplying Rabi frequency from here once with this term. And then we would have the second power of Rabi frequency here. So that would be the kind of higher order term that we are not interested in our derivation up to the first order. So only thing that is left is this first order term in terms of the Rabi frequency omega cosine omega t times exponent I omega naught times t. So this guy arising from this first initial condition term basically there. Or the term that we solved very quickly by using the initial conditions. Okay, so we have something like this, and this is actually like something we can already solve, and we can solve this via integration, and the first order solution then of course would be giving us the kind of like a possibility to calculate the transition amplitudes, and the higher order contributions would give like external physics, basically a rise of energy level and shifts, so-called Bloch-Ziegert shifts would take place if we would solve the system up to a second order in terms of Rabi frequency. But this is basically not where we want to go here. It's enough that we solve this for up to the first order, so that this physics that would happen when we would be solving the system up to a higher orders, this is basically what we are not interested in our course. So we are not interested in kind of like energy levels shifting due to the fact of the perturbation, and we are not interested in any kind of like multi-photon processes or saturation effects that much within the dynamics. So this is not really crucial to understand the behavior of lasers, that for example how some kind of like transition into the excited state starts saturating. So that's enough that we just know that we can raise the electron, and that's fine. So if we would really continuing the expansion, we would notice that there would be a kind of pattern arising, so that the even powers of Rabi frequency omega, they would generate new terms into the C1 term or the kind of CG term, and the odd powers of Rabi frequency would generate new terms into the C2, so basically to the CE excited state terms. Sorry about the kind of confusing label here, that most of the time in the derivation I've been using E and G labels, and now we have 1 and 2 here. Okay, so now what we do get out by solving the system is that we get the dynamics of the excited state. And this is the main interesting thing we want to calculate, that we want to calculate how easy it is to populate the electron into the excited state, and how quickly and how efficiently we can do that with a given incident field. And this we can really understand by looking at the result. So we now have an explicit form for the CE expansion coefficient as a function of time. So that's a minus I omega divided by omega minus omega naught exponent to the power of I omega minus omega naught times t divided by 2 times sine of omega minus omega naught times t over 2. So here we have assumed that we have a so-called monochromatic transition. So we really assume that the incident field is basically monochromatic, and that these frequencies are close to each other, so that we are essentially hitting almost the resonance of our system. So this is the kind of one of the assumptions we need to be able to derive the CE coefficient into this form. And in addition, we use a so-called rotating wave approximation, RWL, here to hold. And this basically just means that we are kind of like mostly interested on the dynamics only of this frequency difference. So we are in a way kind of like a rotating coordinate system at the kind of like close to this omega frequency or omega naught frequency. And we are really mostly interested in about the kind of like their frequency difference and how these different expansion terms differ with respect to the frequency difference, and not really how they are oscillating with respect to the omega frequency or oscillating with respect to the omega naught frequency, but rather we are only interested in the kind of like relatively slow dynamics of the system and not the quick oscillations happening at the omega and omega naught. So that's basically the physical meaning of a rotating wave approximation. And finally, please recall that if you really want to calculate the state population, we can take the square modulus of the CE expansion term, and that would be the means of actually calculating the population. And now we do have this as a function of time, so we can really calculate the population dynamics when we are exciting the system using a pump electromagnetic field. So now basically this equation and taking the square modulo of this term gives us the dynamics. We are hitting our atomic system with an impinging electromagnetic field. We are under electric dipole approximation and all the other approximations we have made. And this is basically giving us the kind of dynamics, how the electron is being raised from the ground state into the excited state. So this is the main thing that we wanted to show to you today, and I hope you enjoyed this quick derivation, and now I will stop here today. Bye-bye.